Hello and welcome everybody to today's seminar presentation in the MIRACUM and DIFUTURE Kolloquium. Today we have two guests from the Erlangen Department of Artificial Intelligence in Biomedical Engineering, short abbreviated with AIBE. I really welcome our two presenters, Arijana Bohr and I don't see her name, sorry. The second.
Emanuelle Salin.
Thank you very much. The title of the presentation is DigiLut, and you can see already the first slide. Some of you might think this is confetti from Fasching and Carnival, but it actually is probably whole slide images from pathology.
Exactly, yes.
That's the topic of today's presentation, where both presenters will present the DigiLut Digital Pathology Challenge. Welcome, and I hand over to your presentation.
Yeah, thank you very much for the introduction. Hello. Today we'll be talking about DigiLut. Emanuelle and we both participated in this international challenge on machine learning. The challenge was to see if we can create an algorithm that is able to detect type A lesions from lung transplant biopsies. So quick facts about us. We are from the Machine Learning and Datenanalytics lab. Our university is the Friedrich-Alexander University, Erlangen. My name is Arijana. I studied mathematics. Right now I'm doing my PhD on the topic of artificial intelligence in medicine research.
My name is Emanuelle. I'm a postdoctoral researcher, and I did my PhD in France on vision language transformers.
Yeah. Together, me and Emanuelle, we're working on the project, the Center for AI in Medicine of Erlangen. The mission of the center is to connect medical experts with machine learning experts, such that we can together solve interesting research questions with machine learning. This was exactly what the DigiLut Challenge was about also. There is Antoine Roux. Antoine Roux is a pulmonologist from Hospital Foch. Hospital Foch is a hospital in France. And Antoine Roux one day sat down and thought, can AI accurately detect type A lesions? He thought about this and he thought, how can we address machine learning experts to help us solve this question? So he thought about it and he came up with this idea. Let's create a challenge. So Emanuelle and we saw this challenge online and we thought, hey, this is very interesting. We want to see if we can maybe develop an algorithm that is able to detect type A lesion. Something that we thought was very intriguing was the huge data set. We had access to 2,000 digitized lung biopsies. 25% of them were annotated. They were annotated by expert pathologists from around the world. Another thing we found very interesting was the possibility of having a translational impact. So maybe with some of the ideas that popped up during this challenge, one could do further research to maybe develop a tool that is able to actually support a pathologist in their everyday work.
So what is precisely the goal of the challenge? So you have a whole slide image from a patient with type A lesions, and you want to detect those lesions to detect graft rejection. So you have the ground truth bounding boxes and the predicted bounding boxes that each competitor will predict. And a bounding box is considered valid if the generalized intersection over union of the predicted bounding box and ground truth bounding box is above 0.5. So this is the first step of the evaluation, and then the next step of the evaluation is to aggregate all the bounding box of the image and of all images. That is done using an F2 score. So the goal of our challenge will be to generate those predicting bounding boxes so that the generalized intersection over union is more than 0.5 with the ground truth bounding boxes. So for this challenge, we created a pipeline in 3 steps. The first step is the creation of the dataset. we go from a whole slide image and we extract from this image smaller patches that we then annotate using the provided bounding box annotations. Then we train patch classification models that are able to, given a patch, decide whether or not this patch contains a lesion. And finally, we use those models to generate predicted bounding boxes. What we do is across the whole slide image, we predict the score of each patch, and then we aggregate those scores to create bounding boxes. So the first step of the pipeline is the creation of the patch datasets. So first, why did we choose this approach? Indeed, the task is a region of interest detection task. And in the literature, there are several approaches, and the main one is the approach of object detection. And there are several models that have been developed in recent years about object detection. For instance, you have the YOLO models that have made a lot of advances in recent years. So you can, for instance, have an image with a frog and accurately detect the frog in image. It's completely possible with current advances. However, this approach is very challenging to apply to very large images. If, for instance, you have a very large image and very tiny frogs in this image, it's much more difficult to detect the frogs in this image using object detection models. So what we do is that we extract smaller patches from this image, and for each patch, we will ask, is there a frog in this image or not? And then we can accurately detect bounding boxes of the frogs. So coming back to the medical domain, this approach of patch classification has previously been used in deep learning and, for instance, in breast cancer research, and is more efficient than object detection because it enables the use of smaller images that leads to smaller training times and smaller inference times. So after deciding to generate patches and to extract patches, the next step is to decide what kind of patches we want. So regarding the size of the patches, we decided on patches of 224 by 224 pixels, just using from literature research, which are standard commonly used patches in computer vision models. But then the next step is choosing the zoom levels. Our whole slide image have 6 zoom levels from level 5 to level 0, which each one is twice as zoom in. So we need to decide which zoom level is the most appropriate to detect if a patch contains a type L lesion. If we had the example of the frog that I gave before, it would be very easy because we can see visually if there's a frog in the image looking at a patch, and we could decide ourselves what zoom level to choose. But since we have limited background in medicine and we do not really know what a type L lesion looks like, we couldn't do it like this. So what we did is we took the statistics of the training datasets and computed the average bounding box of the training datasets and determined that it was similar to the size of the level 2 zoom. So we took the level 2 zoom which was appropriate for the details, as well as the level 3 zoom, which gave a bit more of context for our future approach.
Now that we decided which zoom level to choose, we then had to extract the patches. For example, the image at level 2 was 20,000 by 50,000 pixels on average. These are huge images. However, on average, a machine learning model usually takes 224 by 224 pixels. What we did is we just divided the image into patches. For example, for level 2, this would be around 20,000 patches. For level 3, this would be 5,000 patches. These are still a lot of patches to go through, especially if we look at the big image on the top left. There's a lot of white in the image. So a lot of the patches we would be getting are patches that don't have any relevant information on them. Something we therefore had to do is to only consider patches that have relevant information. So we delete patches that are background or artifact. To do this efficiently and in a timely manner, we use the hierarchical approach. This means we start with level 5. Level 5 is the level where there's not that much detail yet. So we start with level 5, divide level 5 into patches. We start with the first patch and we ask, is this patch an artifact or background? If the answer is no, we look at it with higher detail with level 4. We ask again, is this patch an artifact or background? If the answer is no again, we look at it with even more detail with level 3. We ask again, is this patch an artifact or background? If the answer is no, we now finally select our patch with relevant information. We do this for all patches. Once we have all the patches that have interesting information on them, we label them. For this, we annotate them with soft labels. This is how it looks like. We say if there's a patch that does not have any overlap with a lesion, it gets the value 0. If it does have an overlap with a lesion, it gets the GIOU value of that. Let's look at an example. In the example, you can see a green box. This is the ground truth box. We also see a black box with the letter A. The box A has an overlap with the ground truth box. Therefore, it has a value between 0 or 1, which would be the GIO value of the overlap of box A with the ground truth box. Box B, however, does not have any overlap with a lesion. Therefore, it is getting assigned the value 0. The reason why we use soft labels instead of just binary labels is we didn't just want to know, does the patch have an overlap with a lesion? Yes, no. We wanted to know how much of an overlap does the patch have with a lesion. So once we have now annotated all the patches, we could then create our training dataset. Because there were a lot more patches that do not contain any information about a lesion specifically, we had to select patches smartly. What we did, we randomly selected patches for a 2-to-1 ratio. This means for every patch that has an overlap with the lesion, there's 2 patches where this is not the case. So 2-to-1 ratio.
So the second step is the training of patch classification models in our pipeline. So first, we pre-process the patch. So we adopt kind of a standard procedure where we first enhance the contrast to make the details more visible, and then standardize the luminosity to have to eliminate the contrast among images. Then we augment the data sets using standard and commonly used computer vision approaches, such as flipping horizontally or vertically during the color and applying Gaussian blurs. Once we've done with the pre-processing, we train our model. So the way we chose our model architecture was by testing several pre-trained image classification models. So from convolutional models to transformers, we finally decided based on results on transformer models, such as DynoV2 and SWIN. So you can see on an image on the right, so we first have a patch, then we split this patch into smaller patches that are given to the transformer model. And then using this transformer architecture, we predict the presence or absence of lesions. So the way we decided our transformer architecture was first using open source models and pre-train on open source dataset, because we thought we would only be able to use open source data as the challenge forbid us from using any whole slide image data. So then we also selected the small versions, and this led us, so we selected the small version because this led to reduced training time. So this led us to having faster experiments and faster inference times afterwards. So the main challenge of training our model was the loss to use. If we go back to what Arijana told you, so we have a highly imbalanced data set because we have a low amount of lesions in the whole slide images. So that's the first way this data set is imbalanced. We have more patches without lesions than patches with lesions. But there's another way this data set is imbalanced. Among all our patches, we have a lot more patches which are only slightly overlapping the lesions than patches which are centered on the lesions. Indeed, if we have a look at our data sets, the mean of our patches, the IOU with lesions, would be around 0.1 or 0.2. So this means that our data set is highly unbalanced. So what we do is we use for these data sets an adaptation of the focal loss. The focal loss was first used in object detection to address the class imbalance between background on objects. So what we do is that we adapt this focal loss to our soft labels. If you remember our soft labels, the bigger our soft labels are, the higher the overlap with a lesion. So, which means that our labels model the overlap between patch and lesion. So by adapting our focal loss with those soft labels, we are able to have higher outputs when there is a higher probability of higher overlap with the lesion. So we scale then the labels before computing the loss.
Okay. So now we then trained two models, one model for Zoom level 3 and one model for Zoom level 2. We did this because level 3, the patch classification model, was very fast, but not that accurate. Level 2 was more accurate, but slower. So we combined them to get the best of both worlds, so to say. I'll lead you through this. Okay, so first we look at our whole slide image with level 3 Zoom. We extract the patches from it, and we extract overlapping patches to make sure we get every information in order to detect the lesions. And we then ask our trained patch classification model for level 3 whether it thinks this patch belongs to be part of a type A lesion. The model then gives us scores, probability scores, and we can then set a threshold, for example, 0.5, to say, okay, if a patch has a score above 0.5, we consider it to be part of a bounding box. If patches are quite next to each other and both get high scores, we combine them to one bounding box. Okay, so now we have found bounding boxes with level 3, but like I said, level 3, the patch classification model was very fast but not as accurate, which is why we then use our trained level 2 model to go over the identified regions from level 3 specifically and see, can we refine the bounding box, or is there actually a type A lesion? For level 2, we do the same approach like we did for level 3, which is we generate patches and we ask this time our level 2 patch classification model, do you consider this patch to be part of a type A lesion? We then again get scores, and we then say, okay, the bounding boxes with the highest scores are then the bounding boxes we think are most likely to contain type A lesions. With this approach, we were quite successful. We got a second place in this international machine learning competition. And we are also now going to collaborate with the first place winners and with the expert pathologists from Hospital Foch together on a research paper. The reason why you can see here a difference in the public and private leaderboard from our scores a little bit is that we seem to have slightly overfit on the public leaderboard compared to the private leaderboard. But all in all, this was our approach seemed to be very successful. And
so for future work, we would be interested in exchanging with clinical partners, and we already have started for more feedback. For instance, the way we have selected the Zoom levels was completely based on the statistics of the training data set, and with further feedback from the medical and the pathologists and from clinicians, we could do those sort of choices more scientifically and biologically relevant manner. Then we only had 2 months for this challenge, so it was a bit short on time, and we couldn't really do extensive experiments to explain why some models worked better than others. So another step would be to explain our performances through ablation studies. Finally, we also tried to leverage the non-annotated data, which was 3/4 of the data sets, through self-supervised pre-training during this period. But during the 2-month challenge, we didn't manage to get better results using this non-annotated data. But with more time, we hope that we could leverage this data and pre-train other models using this data to then fine-tune on the supervised data. And finally, we are in discussion with the experts pathologist from the Forsch Hospital. So we hope we could discuss some potential translational possibilities and implementations of our methods. So to give you a bit of an overview of what this challenge looked like, so we only started this challenge in 2024, but it goes back all the way to 2021 when it was selected by the French government as part of a list of potential challenges. And then once it was selected, the pathologists created the datasets. So the way they did it is they used the slides from the Forsch hospitals, but they asked from expert pathologists from all around the world to annotate those slides. So it took quite a bit of time and cooperation. So the challenge itself only lasted 2 months in summer 2024, and then the results were given in afterwards, and all the winners had a talk with the pathologists in November 2024. And from that point on, we started a collaboration with the first winners and with the expert pathologists for a paper and for further collaboration to improve our models and hopefully get better results. So thank you for your attention. We're ready to answer any question you have.
Thank you.
Thank you very much for the very nice presentation of the whole project with the challenge and your final results. Is there any questions from the audience? If not, let me just start. I didn't get at the end the details of the score. What did the score really mean about the quality of the detection?
So medical speaking, those scores are not good enough for use in a clinical setting. I would say it would need to be higher, around 0.6, 0.7 to be able to use. The thing is, this is the first approach, and we had no contact with the pathologists. So we have and only had 2 months to do our models. Mm-hmm. So what we reached, I think, was still like if we compare to the random line, random score, the random would be, I think, if I remember correctly, around 0.07, something like this. So it's much higher than randoms, but still not good enough for a clinical setting. The goal would be to discuss with pathologists and to see how we could improve this to make it usable.
I was just wondering if you measured also some other quality indicators like sensitivity or specificity.
The thing is, in the context of the challenge, we had no way of accessing the public leaderboard at all. Like we only gave our predictions and they gave us the score.
Ah, okay.
This is the only metric that we have access to. What we did was we did have more data on our own patch classification models, and we were able to so have these metrics to be able to judge our models. The thing we didn't manage to judge that much was the aggregation methods. And I think this is where we overfitted a bit in our clustering methods, a bit on the public leaderboard compared to the private leaderboard.
Okay. And have you already got in contact with pathology department here in Erlangen University Hospital, for example, to talk with them about future collaboration?
And not yet. But that would be a good idea.
That's maybe much closer than Paris, even if it's not so nice. Yeah, and also I can see in the audience some medical informatics guys from the Bavarian Cancer Research Center, and one of our focus in AI is also on machine learning on pathology imaging. And so getting in contact with them and sharing experiences would probably be really helpful. Is there anybody with an additional question to Arijana or Emanuelle?
It's me maybe. So I'm the
Yeah.
pathology guy. So I'm not so familiar with graft rejection pathology, also lung, and with the type I lesions. How did you define the type A lesion, or how did the pathology say what type A lesion means, and how, or is there a possibility to use other features of a rejection? Because usually here in our institute, we base our rejection score on several details. Maybe you could have some details on this topic, or so. I'm not so familiar so far. I would be interested.
So from what we were able to gather is they needed lots of meetings with the other pathologists to kind of find an agreement on how they wanted to define the graft rejection. So
yeah, the way they did it is so like we are not really familiar either, but we from the presentations they did is they so annotated bounding boxes of where lesions could be found. So lesions are signs of transplant rejection, of graft and transplant rejection, and the inter-annotator agreement was was around, I think, 0.7. So for what they did for the test set is that they combine lesions where both annotators were in agreement. But since it was much more intensive, they couldn't do it for the whole training set. So they only did it for the test set and not for the training set, which leads us to having a train set that is a bit noisy, with some annotators like annotating in a certain way and others in another way. But that's also part of the data we work with. What happened also is that they didn't have to annotate every single lesion. They only had to annotate some of the lesions in each slide, and this we didn't know before doing the challenge, when we were doing the challenge. So we didn't take into account when doing our methods. But what happens is that on a whole slide image, there can be several layers of the same biopsy, and we had never done digital pathology before, so we didn't really anticipate it. But sometimes the lesion is only annotated in one of those layers and is actually represented in all of those layers, but only annotated in one. So that makes for really a bit noisy annotations. And if we had known that before, I think we could have tried to anticipate it.
Thank you.
Okay, that means the lesion just means, okay, they pointed out a spot where they look at, but they did not precisely give you the information why they choose to focus on this kind of space. Okay, that also explains a little bit the high intervariance between the pathologists.
I think that they had meetings and between them to decide, but there's still a high variance between them.
Yeah, that's also a problem. Pathology usually one thinks that it's very objective, but actually it's very subjective. So somehow we count cells, otherwise it's like a bit, yes, might be this or not. So, okay, but thanks for the interesting talk. And also it's quite complicated with biopsy material. You have to, when it's cut out, it's there, you have lots of artifacts and you don't know where they cut really on it, or whether is it representative for the whole specimen. But thanks a lot.
Thank you.
Is there anybody else with a question? I cannot see anybody. So thank you very much again for the presentation, Arijana and Emanuelle. And I hope I can see most of you also next Tuesday, when we have a presentation from Heidelberg about Erstellung multimodaler Datensätze für föderiertes Lernen mit DICOM-strukturierten Berichten. Wir bleiben also im Bildumfeld und im Bereich Machine Learning, diesmal föderiertes Lernen. Und wir sind gespannt, was die Kollegen und Kolleginnen aus Heidelberg zu berichten haben. So thank you very much for today's colloquium, and I wish you few more hours from Carnival and Fasching Enjoy the day and have a nice week. Bye.
you.
Thank you. Bye.
Have a nice week.